Hi, class. So we were right in the middle of simplifying cube roots, and I don't remember how many we did. So I worked out 4 of them that I thought we did in class, and I left 4 of them that I'm not sure we did. And so we're going to just clean up and practice a little bit more of the cube roots. Then I'm also going to take a few minutes and do the next page, which has some higher roots. Okay, so let's go to the top. Cube root of 250. Now, we can do the cube root in our calculator and check to see, is the cube root of 250 going to come out really nice? Check that. Turns out it's not nice. So we're going to go down to our cube roots. Now, we've only memorized up to 216, well, 1,000, but that's past 250. So 216 is not really like a halfway number. But the next one, 125, is exactly a halfway number. Turns out that factors. So we can take the cube root of 250 and factor it into 125, which is a nice cube root, and times that by 2. Cube root of 2 is not a nice answer. We don't get a clean, easy answer out of it. But this simplifies because part of it is a cube root of 125, which equals 5. And 5 is times. Now there's a times of a cube root of 2, which we cannot simplify. So that is the simplified answer of the cube root of 250. That giant cube root of 250 simplified down to a small cube root of 2 times the whole number 5. Okay, here's a couple more. Let's go to the second row. We got 135. And if we start with the cubes that we've memorized. Now 216 is already too high. 125, I think that's not halfway, so it's going to divide it and leave us a decimal. So we got to keep checking here. Does 64 go into it? No, it's odd, so 64 is even, it can't go in. 27, maybe that. We'll try the calculator. It turns out 27 goes in 5 times. So I'm going to set my cube roots up here. I'm going to do the nice ones in green, the ones that are not nice in red, and 27 does break down 135, and it breaks it down 5 times. Now, that's how we do the numbers. We do the numbers by dividing perfect cubes. Now, we do the variables a little bit differently. We do the variables based on exponents that are multiples of 3, because we have to be able to divide the power by 3. Turns out x to the 6th is a perfect, because 6 divided by 3 is going to have a nice answer. Now, y to the 4th is not. The cube root cannot work with y to the 4th. But we can break y to the 4th down into a y cubed. Now, a cube root can do a y cubed. But that leaves me one extra factor of y. So 27 times 5 is 135, and x to the 6th is all by itself, and y cubed times y is y to the 4th. So that factoring breaks it down, but we've got something we can answer now, because we can simplify the green one. Cube root of 27 is 3, whole number 3. I'm going to make the nice answer in green as well. The cube root of 27 is the whole number 3, no cube root on it. The cube root of x to the 6th. Take the powers and divide by 3. 6 divided by 3 is x squared. And y cubed, the cube root of y cubed is y. Times that by, now this cube root of 5y is stuck. We cannot make that nice. That's the final answer. Okay, let's jump over here to the second one, last one on the second row here. And I'm looking at 192. Okay, now 192. 216 is a little past 192. 125, I don't know, you could try dividing that in. 192 is more like 100, so I think 125 is too big to try. When we divide it, we're going to get something less than 1. But let's go to the next one, 64, and 64 actually goes into it. 64 is a factor of 192, and when I factor it, it goes in 3 times. You try that in your calculator. 192 divided by 64 is 3. So 3 times 64 is 192, but the green one, the square root of 100, the cube root of 64 has a nice answer. Now we've got to attack the variables. Now we attack the variables a little differently. We look for multiples of 3. A cube root of m to the 5th won't work. So we're going to have to break up m to the 5th. But we could break it down by m cubed. And the n's are already cubes. Now if I break m's down by m cubed, I'm going to have m squared left over. Now that we can simplify, because the cube root of 64 is a nice answer 4. Cube root of m cubed is a nice answer m. Cube root of n cubed is a nice answer n. No radical sign. The green one simplifies down to this really nice result. Now the red one, I cannot simplify that cube root. It's stuck. And so that giant square root simplified down to a much smaller square root. Okay, one more of these on the cube root side. Here we got -6. Now we're taking a cube root of 54. We're going to have to break down the 54 if we can. And what number will go into 54? Well, 54, we're going to have to go down to 27 because 64 is too big. So let's try 27. Does it go in? And divide by 54 by 27. Okay, so 27 goes into 54 2 times. That means we can separate or factor down the cube root. So I'm going to make 2 cube roots, one for the nice factors and one for the not nice factors. And the cube root of 27 has a nice answer. I'm not doing the answer yet. I'm just separating the good factors from the bad factors. And the 54 equals 27 times 2. Now the cube root of 2, that's stuck. Can't do that cube root. Now the m's. Oh, I'm sorry, the variables. We need to do the variables, and the variables, we do them slightly different. We do them by looking at the exponents. Cube roots can only undo multiples of 3. 3 has to go into the power, and 3 doesn't go into 8. So we're going to have to break down the m's. But we could break them down into m 6th power times m squared. That makes m to the 8th power. Now the n's are all good. I'm going to put all the n's in the nice one because I can do a cube root of n cubed. The p's are not so nice. I need to make my root a little longer. P to the 7th won't work, but p to the 6th I can do. And if I factor out p to the 6th from p to the 7th, I'm going to have a p left over. Now the green radical I can simplify. When I simplify all the nice cube roots, cube root of 27 is 3. Cube root of m to the 6th is m squared. Cube root of n cubed is just n. Cube root of p to the 6th is p squared. All of that green answer is a nice simple answer. There's no radical on it. I finished the radical. I got the green answer there. Now that is times by the cube root of 2 m squared p. Now that part is stuck. The red one I cannot simplify. I'm almost done. I got one more thing I can do here. 6 is a whole number. -6 and 3 are whole numbers. So we can at least multiply the whole numbers. We get -18 m squared n p squared times cube root of 2 m squared p. Now I'm going to take the square root, the radical, and send it all the way over to the other side. Okay, so there we've simplified some cube roots. Next, we're going to go on and simplify some higher roots. Okay, class, let's do this last example here, last page, of higher roots. Notice some of them are radicals with an index of 4, 4th root. Some of them are radicals with an index of 5, which is a 5th root, and some of them are radicals with an index of 7, they're 7th roots. The game plan is still the same. We need to simplify, and we would take our calculators and check and see if we put them into the calculator, do they come out nice? So we first of all have a 4th root of 625. Now if you know your 4th roots, 1 to the fourth power is 1. That's not that big a deal. 2 to the fourth power is 16. 3 to the fourth power is 81. 4 to the fourth power is 256. 5 to the fourth power is 5 times 5 times 5 is 625. Hey, that is our problem there. So this answer is a perfect. It equals 5. How come? Because 5 to the fourth power equals 5 times 5 times 5 times 5 is 625. So we have a simplified answer because it was an exact value. It was a perfect, I'm sorry, it was a fourth root of a perfect fourth power. Okay, let's go down and look at the second layer down. There's another fourth root. 48. Okay, the fourth root of 48, it's not in our list of perfect fourth powers. And 81 is too big. If anything is going to work, it has to be 16. So take your calculator and divide 48 divided by 16. Well, turns out 16 does go in nicely. We're going to do a fourth root of, and it is times 3. 16 times 3 is 48. Okay, now what about the radical? I'm going to do a little bit of scratch work down here. The fourth root of a fourth power. B to the fourth power. Oh, that equals B. Easy. What about the fourth root of, what's the next one? Well, we're dividing the power by the index. 4 divided by 4 was 1. The next one that's going to work is 8th power, because we can take 8 divided by 4 and we get b squared. So this b here is a perfect. We can do that radical and get a nice easy answer. Okay, so the green ones we factored out. The green factors have nice fourth roots. The red one doesn't. So when we simplify, fourth root of 16 is 2. Oops, wrong color. Because 2 times 2 times 2 times 2 is 16. So the fourth root of 2 to the fourth power is just 2. And the b's, we do the b's a little differently. We divide the exponents. So 8 divided by 4 is b squared. That has a nice, easy, simple answer. Now, we're timesing this by the fourth root of 3. This radical is stuck. I can't do anything with that. It's just, we're just going to have to leave it. So that is our final answer. We just simplified a fourth root problem. Okay, let's change gears and slide over. Let's do fifth roots. Now, to do fifth roots, it helps to know fifth power numbers, like 2. 2 to the fifth power is 32. 3 to the fifth power is 243. Oh, you can't see it. Those are off the screen. 2 to the fifth power was 32. 3 to the fifth power is 243. These are really the only two fifth power numbers. Well, I've got one more. But those are the main two you need to know. It'll help you. Anything bigger than those, if they're fifth powers, just use your calculator and check with your calculator. There is one more fifth power that is useful to know. And I'm going to clean up some stuff here. The other one is 100,000, right over here. 10 to the fifth power equals, has 5 zeros. And so if you do a fifth root of 100,000, it's going to equal 10. These three, if you know these 3 fifths, you know enough for doing fifth root problems. So here we go. First row, fifth root is 64. Now, our perfects are 32 and 243. 64 is not one of them. It's not 8. It's not 4. Those are fourth power numbers or second power numbers. But 64 is not a fifth power number. But 32 goes into 64. So we can factor this down. A fifth root of 32 times a fifth root of 2. Now I'm factoring out the fifth root of 32 because it has a perfect answer. That was the wrong color though. 32 is a perfect fifth power, so the fifth root of 32 equals the whole number 2. Now, the fifth root of 2 is stuck. I cannot make that more simple. That is our simplest answer. Okay, next one down, also a fifth root problem as a -3. And I have a fifth root. I want to start factoring. Now wait, fifth root 32, hey, that's a perfect fifth root of 32. That's our first perfect fifth power. Now, the fifth root cannot work on a sixth power. It won't work. Fifth roots undo fifth powers. They do not undo sixth powers. But we can break the sixth power up into a fifth power times a fifth root of 1 extra x. Because x to the fifth times that extra x does make x to the sixth power. But by separating the x's like this, we get a perfect that we can simplify. So -3 times. Now the fifth root of these perfect fifth powers is 2x. Fifth root of x to the fifth is just x. No radical, just a nice simple answer. Times a fifth root of x that is stuck. Now I do have a whole number coefficient. I have the whole number 2. So I can multiply these and get 6x, fifth root of x. There's the simplified answer. Last two problems. Notice both of the last two are seventh roots. Now, if they did have numbers, you'd have to check their numbers to see if they are perfect seventh power numbers. But neither of these have numbers. So, how do we do them when there's variables? We do the variables slightly different. We do the variables by multiples of 7. So, a seventh, oops, I gotta move this over. Let's see. A seventh root x to the seventh equals x, because I can go 7 divided by 7. A seventh root of x to the eighth, no good. 9th, 10th, 11th, 12th, 13th, no good. But a 14th power, that is simple. Seventh root of x to the 14th equals x squared. Okay, so 7 and 14 are multiples of 7. What's the next multiple of 7? Well, that would be 21, because 21 divided by 7 equals x cubed. Now 25 is too big. It's not 21. But we can separate the x's. So we're going to do a similar trick as we've been doing. We're going to take the seventh root of x to the 21 and factor it out and have a seventh root of x to the fourth left over. Now, the seventh root of x to the 21 is a simple answer, x cubed. But the seventh root of a fourth power, the seventh root can't touch the fourth power. It just can't do anything nice to it. So we're going to have times a cube root of x to the fourth. That's the best we're going to do, which is actually pretty good. We had a big seventh root of 25th power, and now we have a much smaller seventh. Error. I have an error there. Do you see that? It's not a 3. It's supposed to be a seventh root that we're doing. Now, the seventh root of x to the 21 is a 3. That is correct. But the seventh root needed to be on the radical there. Okay, one last one. Also, the last one is all variables. Now, I can do 14th powers, and I can do 7th powers. That's it. Seventh root only does 7th powers, 14th powers, and multiples of 4. And that means I can break this up. I can have a nice 7th root, and I'm going to have seventh root of some leftovers. L to the 14th is going to have a nice seventh root. M to the 10th, nope, the seventh root cannot do the 10th power. But if I separate the m's and a seventh power of m times a third power of m, that factors it, and I can do the mth root, the seventh root of m to the 7th. Same trick with the n's. N to the 7th I can do, but that means I have to break out 7 n's from n to the 11th power, which means I have n to the 4th power left over. Now, all of these guys are nice. I can do easy radical of all of them. Divide by 7. The 7th root of L to the 14th power is L squared. The 7th root of m to the 7th is just m. 7th root of n to the 7th is just n times. Now the 7th root of m cubed is stuck. I can't make that better. The 7th root of n to the 4th is stuck. I cannot make that better. That is the final simplified answer. This lesson is very mechanical. It's all about figuring out how to simplify radicals. Practice this stuff. I'll see you in class soon. Bye-bye, everybody.